Space radiation presents one of the most significant challenges for astronaut safety during space missions, particularly for long-duration stays on the International Space Station, missions to the Moon, and planned manned missions to Mars. Radiation in space comes from three primary sources: particles trapped in the Earth's magnetosphere, particles from solar wind, and galactic cosmic rays, GCRs, which originate outside our solar system. Protecting astronauts from these radiation sources involves a combination of spacecraft design, operational procedures, and potentially pharmacological interventions. Understanding space radiation is composed of a mix of high-energy protons, heavy ions, and secondary particles produced when primary radiation interacts with spacecraft materials or the bodies of astronauts themselves. The Earth's magnetic field provides substantial protection to astronauts in low Earth orbit by trapping many charged particles. However, as missions move beyond this protective shield, the exposure risks increase significantly. GCRs, which are highly energetic and come from all directions, pose a continuous and unpredictable threat, and their effects can be exacerbated by solar particle events, SPEs, or solar flares that release large quantities of energetic particles. Health risks from space radiation. The health risks of space radiation are severe and diverse. At high doses, radiation can cause acute radiation sickness, while lower doses over prolonged periods increase the risk of cancer, cardiovascular disease, and damage to the central nervous system. Space radiation also poses risks to the skin, eyes, and reproductive organs, and can potentially cause acute effects that might jeopardize mission success. Moreover, the complex and penetrating nature of space radiation makes it difficult to shield effectively against all particles, especially high-energy galactic cosmic rays. Radiation shielding technologies. Traditional shielding materials used on Earth, such as lead, are not practical for space use due to their weight. Instead, spacecraft are typically shielded with lighter materials like aluminum. However, aluminum provides limited protection and can produce secondary radiation when struck by high-energy particles. Advanced materials such as hydrogen-rich plastics and novel composites are being explored because hydrogen is particularly effective at blocking some types of space radiation. Researchers are also investigating the use of water or polyethylene tanks around crew habitats, both of which contain hydrogen, to absorb radiation. Another innovative approach includes magnetic shielding, which would use magnetic fields generated by superconducting magnets to deflect charged particles away from spacecraft, mimicking Earth's protective magnetosphere. Architectural and operational strategies. Beyond material solutions, spacecraft design and mission architecture can be optimized to reduce radiation exposure. This might involve the strategic placement of fuel, water, and waste storage to create additional protective barriers around crew quarters. Mission planning can also be aligned with solar activity cycles to minimize the risk of solar radiation storms, and operational protocols can be developed for astronauts to retreat to shielded areas during periods of high radiation activity. Pharmacological protection. There is ongoing research into pharmacological methods to protect against radiation. These include antioxidants that reduce the effects of radiation on cells, drugs that promote the repair of DNA damage, and compounds that could help mitigate the acute and long-term biological damage caused by radiation exposure. The development of these drugs is complex, as they must be effective against a broad spectrum of radiation-induced injuries without causing harmful side effects. Monitoring and real-time assessment. Effective monitoring systems are crucial for managing radiation risk. Wearable dosimeters can provide real-time radiation exposure data, allowing for dynamic management of astronaut activities to minimize doses. Space agencies are also developing more sophisticated models to predict SPEs and GCR flux, which can help in planning spacewalks, extravehicular activities, and other mission-critical operations more safely. Challenges and future research. Despite advancements, significant challenges remain in protecting astronauts from space radiation. The variability and unpredictability of space radiation, combined with the technical and financial constraints of developing better shielding and drugs, make this a particularly tough problem. Future research needs to address not only improved shielding materials and designs but also more effective operational countermeasures and potentially the genetic or biological enhancement of astronauts themselves. In conclusion, protecting astronauts from space radiation is a multifaceted challenge that spans physics, materials science, medicine, and mission planning. As we push forward with plans to send humans deeper into space than ever before, The solutions to these challenges will be critical to the success and safety of these pioneering missions.